So now that we've talked about what intermolecular forces are, let's take a look at what creates these intermolecular forces and how we determine what intermolecular forces we have present within a molecule. So the first intermolecular force that we're going to look at are ion-dipole interactions, and those are approximately 15 kilojoules per mole of energy. Ion-dipole interactions are very easy to identify because we need at least two things. We need to have ions in solution. So here we have a sodium and a chloride ion, and then we need to have a molecule that has a permanent dipole. Water has a permanent dipole. If we take a look at water, we have oxygen bonded to hydrogen. Oxygen is much more electronegative than hydrogen. Because of that difference in electronegativity, oxygen is able to pull electron density away from hydrogen and toward itself. And so if we were to look at that molecule of water, we're going to have a slight imbalance of electron density. I'm going to have slightly more electron density on the oxygen, giving me that partial negative charge because the electron density is more centered around the oxygen. And because we've stolen some of the electron density from hydrogen, that creates a partial positive charge on the hydrogens. So this is a dipole, an imbalance of charge, partial imbalance of charge. And if we take a look at how water has associated itself around these different ions, we notice that the hydrogens are attracted to the chloride and the oxygens are what are attracted to the sodium. So the hydrogens, because they have that partial positive, they are electrostatically attracted to the full negative charge on chloride. And so our ion-dipole interactions are these interactions right here between the chloride anion and the dipole on hydrogen. And then we're going to go and look at the sodium now. We see the same thing. We see that for the sodium, oxygen has associated itself around the sodium, and that's because the oxygen has a partial negative charge. It has excess electron density. And because it has that partial negative charge, it can help stabilize the full positive charge from sodium through this electrostatic interaction. So we're able to bring sodium chloride into solution because we're replacing that ionic bond, the electrostatic attraction between the sodium and the chloride, we're replacing that with these ion-dipole interactions. So to have ion-dipole interactions, you need to have ions in solution. We need to have something ionic in solution as individual ions. And just as a little reminder of where does this polarity come from, the polarity comes from differences in electronegativity. And so here's the electronegativity trend. And remember, electronegativity is the ability to pull electron density toward an atom. So fluorine is the most electronegative element. It's the strongest element in its ability to pull electron density toward itself. And the general trend is that electronegativity increases from the lower left-hand corner to the upper right-hand corner, with fluorine being the most electronegative. So that's what we need to have a polar bond. We need to have a difference in electronegativity. And so in general, if there is less than 0.5 difference in electronegativity, the bond is nonpolar. So that would be, anything that's bonded with itself. So hydrogen, for example, where I have hydrogen bonded to hydrogen, that's obviously nonpolar because the electronegativity of hydrogen 2.1, so there's no difference because it's hydrogen bonded to itself. Even carbon to hydrogen bond, that's also nonpolar. That's got a difference of 0.4. So basically, the closer things are together, the more similar their electronegativity is, and the more likely they are to be nonpolar. If I have a difference in electronegativity of 0.5 to 1.9, then this is a polar bond. So taking a look at a fluorine bonded to carbon. That difference, fluorine is 4, carbon is 2.5. That difference is 1.5, right? So that is a polar bond because that 1.5 difference in electronegativity that's between 0.5 and 1.9, that is a polar bond. That means I'll have an imbalance of electron density. That means fluorine being more electronegative pulls the electron density toward itself, making that polar bond. And then if we have a difference in electronegativity greater than 1.9, the bond is no longer covalent. We have an ionic bond. And so we notice, again, to repeat that the closer things are together, the more similar their electronegativity is, the less likely it is to be a polar bond. So the farther atoms are apart on the periodic table, the larger the difference in electronegativity, and the more likely it is to have a polar bond. Taking a look at something that would be ionic, right? Potassium is 0.8, fluorine is 4. We've got a large difference. I've got a difference of 3.2 in my electronegativity. That's an ionic bond. These differences in electronegativity also help us understand dipole-dipole interactions. So our dipole-dipole interactions, they are between two permanent dipoles. So I need to have a polar molecule. I need to have something with low electronegativity bonded to something with greater electronegativity to create that permanent dipole within a molecule. So we need to have a permanent imbalance of electron density within a molecule. And as a result, that'll create a molecule that is permanently polar. So we could take a look at a carbon-fluorine bond. That would be a polar bond because fluorine is much more electronegative than carbon. And what that creates is I'll have a permanent imbalance of electron density because fluorine is able to pull that electron density closer to fluorine and away from the carbon. That'll create a partial positive charge on the carbon, which will line up with the partial negative charge that's created on the fluorine when the fluorine pulls that excess electron density toward itself. And so an ion-dipole interaction is simply that. It's going to be the attraction between the partial positive on the carbon and the partial negative on the fluorine. So there's my ion-dipole interaction. I need to have a polar molecule, so I need to have something that's electronegative bonded to something that's less electronegative to create that permanent imbalance of electron density, that permanent partial charges assigned to the molecule. That's going to help create these dipole interactions that come in at around 10 kilojoules per mole in energy. So you're going to have to ask yourself, do I have a polar molecule? If so, then yes, I have dipole-dipole interactions. So let's take a look at some of the impacts of dipole-dipole interactions. Dipole-dipole interactions are very important in helping determine the boiling point of a sample. And if we start with propane right here, we see that there's a very small dipole moment. That means there's a very little imbalance of charge. So there's not much dipole-dipole interactions because it's a relatively nonpolar molecule. That results in a boiling point of 231. As we go down this list, we have a larger and larger and larger dipole moment, which means we're going to have a larger and larger imbalance of charge on the molecule. That means my partial positives and my partial negatives are getting bigger and bigger and bigger, and that's going to allow for more attraction within the sample. If I have more attraction, right, that results in an increase in the boiling point of the sample, because to take that sample from the liquid phase to the gas phase, we have to break all of these dipole-dipole interactions. We have to break all of those intermolecular forces that are holding the sample in that liquid phase. The stronger those interactions are, the more energy we're going to have to put into the sample, and the higher the boiling point will be. So the more polar the molecule, the stronger the dipole-dipole forces, and that's going to result in a higher boiling point. So just taking one more look at this series. This series, we have approximately the same molecular weight, or very close to the same molecular weight through the entire series. I can use molecular weight to determine relative boiling points if I have the same intermolecular forces. So here, all the molecular weights are within the same range. That means I can't use molecular weight to help me determine the boiling point. What I'll have to look to is dipole moment and how polar these molecules are. So the more polar the molecule is within this sample, the larger the boiling point will be. London dispersion forces are the next force that we're going to look at, and they come approximately 1 kilojoule per mole. So they're the weakest intermolecular force. However, they are the intermolecular force that every molecule has. Every molecule has access to London dispersion forces. London dispersion forces are similar to dipole-dipole forces in the sense that they're an attraction between molecules. They're different, though, in that they are only a temporary attraction. And London dispersion forces result from a temporary imbalance of electron density. From a molecule that is temporarily polarized, we can get a temporary attraction that's there 1 second and then gone the next. And so how that might start, right? We might have a helium atom, and then let's just say that this helium atom randomly, both electrons end up on the same side of the helium atom. What that's going to do is expose this positively charged nucleus that has 2 protons in it. It's going to expose that positively charged nucleus to the helium atom next to it, which will attract the electrons in the helium atom next to it. And so we're going to get a temporary imbalance of electron density. And so temporarily, this electron swings to the left, and that gives us this electron imbalance where we have now a partial negative charge on the left side of the helium, and that gives us a partial positive charge on the right side. What that's going to do is induce a dipole in the helium atom next to it, right? It's going to attract the electrons from that helium atom. Right here are my 2 electrons. It's going to attract those 2 electrons, pulling them to the left, generating a partial negative on the helium next to it and a partial positive. And this would go on and on and on. But again, it's temporary because just temporarily this electron swings to the other side and is out of balance. So it's there 1 second and it's gone the next. So those are London dispersion forces. Because all molecules have electrons, right? All molecules have London dispersion forces. The key is it's a temporary force of attraction between a temporary dipole. So that temporary dipole is what I described when I talked about this electron temporarily flipping to one side of the molecule. That temporarily causes a dipole, and that's going to induce a dipole on the second molecule. It's going to pull those electrons to one side of the other molecule, causing that temporary interaction. So the induced dipole is the dipole that's what's set into place by the initial temporary dipole. So all molecules, and this is very important, have London dispersion forces, right? Abbreviated LDF. These London dispersion forces, yes, are the smallest force we've looked at 1 kilojoule per mole, but they are very important because all molecules have London dispersion forces. London dispersion forces are not equal. They will change as we talk about different elements. And so to exemplify that, we're going to look at this series of halogens. We're going to look at fluorine, chlorine, bromine, and iodine. So all 4 of those are halogens, but they differ in their ability to have London dispersion forces. And to think about this, we need to think about the size of the electron cloud for each of these. And it's going to be our polarizability, basically our ability to distort that electron cloud. So the larger the electron cloud, the more London dispersion forces the atom will have. And how we want to think about this, we want to think about the fluorine as this tiny, rock-hard golf ball. It's really hard to push that electron density around because fluorine is the smallest atom in this series. Because it's the smallest atom and has the smallest electron cloud, those electrons are closest to the nucleus. They're feeling the attractive pull of the nucleus the most. Chlorine would be next, but chlorine is a little bit bigger. And then bromine would be next. Bromine is even bigger. And then iodine would be last, and iodine is even bigger. And the importance of that is, here's our nucleus, right? These outermost electrons are farther from the nucleus, and because they're farther from the nucleus, they're not held on as tightly. It's going to be easier to push these electrons around. It's going to be easier to create an imbalance of this electron density. That is polarizability. So how easy is it to distort that electron cloud? The larger the electron cloud, the softer that electron cloud is, the easier it is to push that electron density around. So if fluorine was our golf ball, right, iodine's going to be a giant beach ball, that it has some compression. It has the ability to shift that electron density around because it's a large electron cloud that is much farther from the nucleus in iodine than it is in fluorine. So if I were to rank the polarizability, right, fluorine would be the least polarizability, chlorine would be next, bromine would be after that, and then iodine would be the most polarizable atom available. And again, that's just the ability to shift electron density. The easier it is to shift that electron density, the more London dispersion forces we will have for that atom. So here's an example of London dispersion forces at work, right? I said everything experiences London dispersion forces. So I also try to incorporate examples of chemistry in our everyday life, just because I know many of you are not majors, but I want you to know that whether you're a chemistry major or not, we all experience chemistry every day. So answer the question, how can a gecko walk up the side of the wall? Well, the answer to that question is London dispersion forces. Gecko have these feet with these patterns and these little microsetae. The microsetae are these tiny little hairs that look like Velcro. They've got a little hook at the end of them. The importance of these tiny little hairs, if we take a look at them, is the surface area. They have this giant surface area, and they're able to maximize that surface area on their foot so that each time they're stepping on a surface, they've got this incredibly large surface area where they're taking advantage of London dispersion forces. An incredibly weak force, but it's a cumulative force. So by maximizing their surface area, they're able to maximize all the points of contact with the surface they're trying to walk up, whether it's a wall or a glass surface or a ceiling. By increasing the points of contact, they're increasing all the opportunities for London dispersion forces, increasing the attraction between that gecko's foot and the surface it's trying to walk up. And so there are material science labs right now in the US that are trying to take advantage of this science or trying to understand these attractions in a way so that a material that you could put on and use to walk up the side of the building like you were Spider-Man. All from the microstructure that geckos use on an everyday basis. So if we understand that structure, we can take advantage of that structure, the properties of that structure, to use that to our advantage. Something else we want to think about when we're thinking about London dispersion forces and the impact of London dispersion forces are the shape of the molecule. So I've got N-pentane and I've got neopentane. These are just isomers of the same molecule. And so pentane is a 5 carbon, so it's C5H12. Neopentane has the same formula, C5H12. So same number of carbons, same number of hydrogens, same molecular weight, and yet N-pentane has a larger boiling point than neopentane. Both molecules contain nothing but carbon and hydrogen, so both molecules only have London dispersion forces. So because I only have access to London dispersion forces, I cannot explain the difference in boiling point by saying I have a difference in the strength of the intermolecular forces. How can I then explain that difference in boiling point? Why does pentane have a higher boiling point than neopentane? We can think about it by thinking that London dispersion forces are a lot like friction. N-pentane is a flat molecule, so I can stack many molecules on top of each other, maximizing the surface area for these London dispersion forces. By maximizing the surface area for London dispersion forces, I'm going to have more London dispersion forces, and that means I'm going to have to put in more energy to break those interactions to take the sample from a liquid phase into the gas phase. Neopentane is more spherical in shape, and because it's more spherical in shape, I'm only going to have fewer opportunities, fewer contact points for these intermolecular forces. So flat molecules, right? Flatter molecules have a larger surface area. And that's going to allow for greater contact between molecules and it's going to result in more London dispersion forces. If I increase the London dispersion forces, I increase the boiling point of the sample. Right? More London dispersion forces equals more energy needed to pull a liquid sample apart. And that's what we do when we're taking it from the liquid phase to the gas phase. When we're boiling something, we're separating those molecules. So we have to break all of those intermolecular forces. The more intermolecular forces I have between a molecule, the more energy I have to put in, the higher the boiling point will be. So we have to take a look at the shape of the molecule as well. If the shapes of the molecules are all approximately the same, but we have different boiling points, then I need to take a look at the molecular weight of a molecule. Let's think about that. As I get a larger molecule, larger molecular weight, I'm going to have more protons. More protons means I'm going to have more electrons. More electrons means I'm going to have more opportunities for London dispersion forces because I just need an imbalance of electron density. So larger molecules, right? Larger molecular weight. More electrons. And more electrons allow for more London dispersion forces. I'll have more opportunities to get those electrons out of balance. Taking a look at that series, here's the molecular weight of diatomic fluorine, chlorine, bromine, and iodine. So as I get an increase in molecular weight, I go from 38 to 71 to 159 to 253. I see an increase in the boiling point. I go from 85 Kelvin all the way up to 457 Kelvin, only by increasing the molecular weight, right? All of those samples are nonpolar samples, so I'm not changing the intermolecular forces, but I'm changing the molecular weight, larger molecular weight, more electrons, more attraction between each of those molecules, higher the boiling point. And that works for the noble gases too, right? We think of the noble gases as non-reactive, but they still have different boiling points. And I can determine that, I can explain that by looking at an increase in molecular weight. It's going from helium at 4 AMU to xenon at 131 AMU. My boiling point goes from 4 Kelvin all the way up to 166 Kelvin because larger molecules have more electrons, which result in more London dispersion forces and higher boiling points. So now, going back to where we started, taking a look at diatomic chlorine, that's a gas, diatomic bromine, that's a liquid, and diatomic iodine, that's a solid, how can we start thinking about that? How can we start explaining why we have a gas and a liquid and a solid all under the same conditions, all at standard temperature and pressure? And it goes back to the London dispersion forces, right? With chlorine, I've got a decent amount of London dispersion forces. Bromine, I've got greater London dispersion forces because I've got a larger electron cloud. I go from 17 electrons with chlorine to 35 with bromine and 53 with iodine. Larger and larger electron cloud, more London dispersion forces holding those molecules together. So just going from chlorine to bromine, that's enough to take it from a gas phase into the liquid phase. And then going from bromine to iodine, that increase in London dispersion forces is enough to pull the molecules even closer together, going from a liquid phase into the solid phase. So I can explain the fact that those three halogens all take different phases under the same conditions because of increasing London dispersion forces as I go down that group from chlorine to bromine to iodine, holding the molecules closer and closer together, going from gas to liquid all the way to solid. So in summary, it's not always easy to tell what intermolecular force is the most important, but these two guidelines will help you figure out what intermolecular force should I be thinking about when I'm trying to determine the properties of a molecule that I'm looking at. So if you're comparing molecules of similar size and shape, so if they have the same molecular weight, but they have different boiling points, then you want to think about it's due to the strength of the intermolecular force. So do I have stronger forces present in one molecule than the other? So do I have one molecule that only has London dispersion forces and another molecule that has London dispersion forces and dipole-dipole forces? Well, if that's the case, I'd expect that molecule to have a larger boiling point. However, if you have molecules of drastically different size, so molecules that have widely different molecular weights, then I would look to London dispersion forces. Larger molecules have more electrons are going to result in more London dispersion forces, and that's going to determine the boiling point of the sample.